Good morning, friends. In today's session, we will discuss about the topic unit step function. It is also known as Heaviside unit step function or Heaviside function. Unit step function denoted as u of t minus a or h of t minus a. This is a just notation, that is not as addition subtraction of t and a. U of t minus a is a notation of unit step function or Heaviside unit step function. It is defined as if a is any positive real number, then 1 for t greater than a, and for t less than a it is 0. So that means a is real positive real number, then right side to the a function's value is 1 and left side to the a it is 0. So that is our discontinuous function. If we are taking a equal to 0, then u of t minus a becomes u of t or h of t equal to 1 for t greater than 0 and 0 for t less than 0. That means this side function's value is 1 and left side it is 0. If we multiply some function ft with unit step function, then this ft is multiplied with 1 and 0. That means functions is ft into t of u minus a equal to 0 when t less than a, and ft is ft when t greater than a. Now we will see the Laplace of unit step function. What is the Laplace of unit step function? This is the definition. It is obtained by definition. So first of all, u of t minus a or Laplace of h of t minus a is equal to Laplace by Laplace definition, integration 0 to infinity e raised to minus st ft. Here ft is our function, unit step function. So u of t minus a dt. Now unit step function is u of t minus a, where t less than a it is 0, t greater than a it is 1. So we are dividing this integration 0 to infinity in two parts, 0 to a e raised to minus st u of t minus a plus a to infinity. This is the integration from a to infinity, and between 0 to a function's value is 0. So e raised to minus st 0 dt. So this integration is 0, and between a to infinity function's value is 1. So integration is of this part is here e raised to minus st upon s, and this integration is 0. So I am not writing here 0. Now what is the upper and lower limit? Upper limit is infinity and lower limit is a. So when we are putting the upper limit e raised to minus infinity, e raised to minus infinity is 0, and lower limit a to e raised to minus as upon minus s. Minus minus plus, the final answer is e raised to minus as upon s. So this is the Laplace of unit step function u of t minus a. If we are taking a equal to 0 both sides, then Laplace of ut, that means the Laplace of 1 equal to 1 by s. Now let us see unit step functions second shifting theorem. What is the second shifting theorem? If this is a statement of second shifting theorem, if Laplace of ft is phi of s, then Laplace of u of t minus a into f of t minus a. Here we are not taking f of t, but it is a Laplace of u of t minus a, which is unit step function, and f of t minus a, not we are writing f of t, is equal to e raised to minus as into phi of s. Here phi of s is the Laplace of ft, not Laplace of f of t minus a. So remember this part properly. Laplace of u of t minus a into f of t minus a equal to e raised to minus as phi of s. That is our second shifting theorem. How to prove it? So let us see. It is just by definition Laplace of u of t minus a into f of t minus a equal to integration 0 to infinity e raised to minus st f of t minus a into u of t minus a. Now divide into two parts, 0 to a. This part is totally 0 because unit step function is 0 in this part. So this part is totally 0. And a to infinity, this is our second part of unit step function e raised to minus st f of t minus a unit step function u of t minus a. In this part function unit step function t minus a will be 1. So I am writing here 1 and this part is 0. The integration of this part is 0 and integration a to infinity e raised to minus st f of t minus a into 1. Now we have just only this part because this part is 0. So e to infinity e raised to minus st f of t minus a. Now we are taking the t minus a equal to v, then dt equal to dv because a is constant, and limit of t is a to infinity. When we are putting a, so v is 0 to infinity, so this limit will be changed 0 to infinity e raised to minus v plus a. It is v plus a because t equal to t minus a equal to v, that implies t equal to v plus a. Here we can write t equal to v plus a. So this part is t e raised to minus st t v plus a f of v dv. We are separating this part e raised to minus sv and e raised to minus as. E raised to minus as is totally constant. We are taking outside because this is the integration with respect to v. So this portion is constant, take outside, and final answer is phi of 0 to infinity e raised to sv fv dv. It is a Laplace of fv. Fv means ft. So Laplace of ft is given phi of s. So your answer is e raised to minus as into phi of s, because this portion is a Laplace of ft or fv. So here we will use this theorem in examples like this. This is our theorem. If Laplace of f of t minus a u of t minus a equal to e raised to minus as upon phi s. This is our original theorem. So in this theorem, if we have a f of t minus a, then we are taking here Laplace of ft. If we have a unit step function is constant as it is, there is no change in unit step function, but this function is f of t minus a, then right hand side we are taking the Laplace of f of t. Then Laplace of ft u of t minus a equal to, if we have a f of t here, not f of t minus a, there is some difference between this. Then for the Laplace example, we are taking e raised to minus as Laplace of f of t plus a. If you have a f of t here, then we are taking f of Laplace of f of t plus a. If we have a f of t minus a here, then we are taking Laplace of ft. So that is a major difference. We will use the this formula for examples. And for the inverse Laplace, we are taking, if Laplace of this part is this, if Laplace of f of t minus a unit step function t minus a is e raised to minus as phi of s, then inverse Laplace of this part is e raised to minus as phi of s, f of t minus a u of t minus a. So this is formula to find inverse Laplace function, and these are the formula to find Laplace functions. Let us see examples of second shifting theorem or unit step function. First example, find the Laplace of t minus 1 square unit step function t minus 1. So we have a function ft and unit step function t minus a. This is our second shifting theorem. For example, so f of t ft into u of t minus a equal to e raised to minus as. We are taking Laplace of t plus a here because we have a ft. If we have a f of t minus a, so we are taking here Laplace of f of t. But here we have a ft, so we are taking Laplace of f of t plus a. So in the Laplace example, we are adding a, and in the inverse Laplace example, we subtracting a. Here a is equal to 1 and f of t is t minus 1 the whole square. We need a f of t plus a, that means f of t plus 1. F of t plus 1, that is f of t plus a, is equal to this function plus 1 the whole square. So f of t plus 1 minus 1 the whole square. We replace t by t plus 1 in this case. Here t, we are replacing t plus 1 and then take the square. 1 cancel, then we get only t square. Laplace of t minus 1 whole square into unit step function t minus 1 equal to e raised to minus s, because a is 1. So in this formula we are putting the value of a and f of t plus a, so e raised to minus s and a equal to 1. Now f of t plus 1 is t square, so e raised to minus s and t square, e raised to minus s gamma of 3 upon s cube. It is a Laplace of t square, and gamma of 3 is equal to 2 factorial e raised to minus s upon s cube. So final answer is this. So we are dividing into three parts. First of all, this is the step number 1. It is a formula of second shifting theorem. Now in the step number 2, we are finding the ft plus a and a. Now this is step number 2. Put the value of a and ft plus a. So this is step number 2. So we are writing always in 2 steps. Second example, Laplace of e raised to minus 3t unit step function t minus 2, ft equal to this function e raised to minus 3t and unit step function u of t minus a. So according to the theorem, second shifting theorem, it will be e raised to minus as, and here we have a ft, so we are taking here f of t plus a. If a equal to 2 and ft equal to e raised to minus 3t. So this is step number 1. F of t plus a equal to f of t plus 2. Therefore, e raised to minus 3t plus 2, e raised to minus 3t minus 6, that will be separated, and we get e raised to minus 6 and e raised to minus 3t. So that is our f of t plus a. ft into unit step function t minus a, we are putting value of a in the second shifting theorem. This part we will put value of a in this function. So a equal to 2. So this is f of. So this is our second step. Step number 2. F of t u of t minus 2 e raised to minus 2s a equal to 2 and f of t plus 2. Laplace of f of t plus 2 e raised to minus as. F of t plus 2 is this function. F of t plus a, that means e raised to minus 6, e raised to minus 3d, and e raised to minus 6 come outside, and remaining part is Laplace of e raised to minus 3t only. Now this is e raised to minus 2s plus 6, combine them, and Laplace of this portion is 1 upon s plus 3. So final answer is e raised to minus 2 s plus 3 upon s plus 3. We are taking here 2 common from this portion. So that is our final answer. Laplace of e raised to minus 3t unit step function t minus 2 into the equal to e raised to minus 2 into s plus 3 upon s plus 3. Let us see one more example here. Laplace of t square unit step function t minus 2. So first of all, write down the formula of second shifting property. Laplace of ft u of t minus a equal to e raised to minus as f of t plus a, because we have a ft here. When we have a ft, then we are taking Laplace of t plus a. If we have a f of t minus a, we are taking Laplace of ft. In the most of example, we are using this formula. That is the second shifting property. In this case, this is our step number 1. Now, where a equal to 2 and ft equal to t square, then f of t plus a, it will be f of t plus 2 equal to t plus 2 the whole square, and its square is t square plus 4t plus 4, expansion of this whole square. Now Laplace of ft, f of t minus a, we are putting a equal to 2 in this equation. Then Laplace of t square, second number step. Step number 2, put the value of a and solve it. So first of all, t square is our original function in the question, and f of t u of t minus 2 a equal to 2. So right hand side will be e raised to minus 2s. We are putting here a equal to 2 and f of t plus 2. Our new function f of t plus 2 is this. This is our new function f of t plus 2. So e raised to minus 2s Laplace of t square plus 4t plus 4. Individually find the Laplace of each term. Laplace of t square is gamma 3 upon s cube. 4. Laplace of t is gamma 2 upon t square. We increase the 1 power, and 1 Laplace is 1 by s. So finally t square unit step function t minus 2 equal to e raised to minus 2s 2, because 3 gamma 3 is 2 factorial, so it is a 2 upon s cube. It is 4 upon, because gamma 2 is 1 factorial, so it is 4 upon s square and 4 by s. So that is our Laplace of t square into unit step function t minus 2. Let us see one more example. Laplace of sin t into unit step function t minus pi. Here ft is sin t and unit step function t minus a, so a equal to pi. And according to the second shifting property, this will be our formula. Laplace of ft equal to u of t minus a equal to e raised to minus as f of t plus a, because we have a ft here. A equal to pi and ft equal to sin t. F of t plus a becomes f of t plus pi, that is sin t plus pi. Sin t plus pi is minus sin t, because this is the third quadrant. Here we have a third quadrant. So this is our step number 1. Now Laplace of the second step number 2, find the Laplace of original function sin t u of t minus pi. So it will be e raised to minus pi s because a equal to pi. Laplace of f of t plus pi is e raised to minus pi s. Laplace of minus sin t, minus come over outside, and Laplace of sin t is 1 upon s square plus 1. So finally answer is minus e raised to minus pi s upon s square plus 1. So this is the second shifting property in the Laplace transformation. There is a second shifting property in also inverse Laplace transformation. These examples we will see in the next video. Thank you for watching.